Hi everyone, I'm Kfir Sulimany from the Hebrew University of Jerusalem. I'm a PhD student in Yaron Bromberg's group for complex photonics, and today I'm going to introduce an all-fiber source and sorter for multimode correlated photons. This talk is based on this paper on arXiv, which will be published soon on NPJ Quantum Information. Let me begin by the motivation for high-dimensional quantum information processing. Most quantum information protocols are based on binary encoding. For example, we can encode states belonging to a two-dimensional Hilbert space like this two-spin system. However, we can also use higher dimensional Hilbert spaces. Implementation based on encoding states in the transverse spatial modes of photons are promising due to the large Hilbert space they span. High-dimensional encoding provides higher capacity and resilience to noise. To see the benefits, let's look on a specific example of the secure key rates of quantum encryption versus the bit error rate for different dimensional encoding sizes. In 0-bit error rate, we just get the classical enhancement of the capacity, which scales logarithmically with the dimension. But each curve has a cutoff in a certain bit error rate. That means that in order to use quantum information for encryption beyond this cutoff, we must use higher dimensional encoding sizes. In the last few years, multimode fiber have been raising lots of interest in a wide range of optical disciplines. In the context of quantum optics, multimode fiber have been used for transport of high-dimensional entanglement and also to implement reconfigurable quantum networks for quantum computing. The leading approach for generating entangled photons in the transverse spatial modes are through spontaneous parametric down conversion in a bulk crystal. And an alternative of coupling the high-dimensional photons to the fiber is to generate the photon inside the fiber in spontaneous four-wave mixing. Therefore, multimode fiber are also interesting as sources for high-dimensional photon pairs. In my talk, I'm going to focus on the ability to generate and sort entangled photon pairs inside the fiber in order to implement high-dimensional quantum information protocols. Let's get a better understanding about the challenges in multimode quantum communication, and specifically with optical fibers. Quantum protocols with photons are based on two main parts. The first is the source, and the second is the measurement. Traditionally, the source of high-dimensional entanglement is based on spontaneous parametric down conversion in a bulk crystal. As you can see here in this seminal work by Zeilinger from Nature 2001, here they pumped a nonlinear crystal to generate photon pairs, and the photons are entangled in their transverse spatial modes. Here, they use projective measurement by spatial light modulator. The spatial light modulator is projecting a specific spatial mode of the photon to a eigenmode of a single mode fiber before the measurement. Now two problems raised. The first is that the projection efficiency is inversely proportional to the dimension we use. And secondly, free space modes are not compatible with optical fiber guided modes. In this walk, I'll try to convince you that we can do both tasks, the source and the sorting of the photons, all with an all-fiber configuration with multimode fiber. Here you can see our scheme for all-fiber source and sorter for multimode correlated photons. Our scheme is based on pumping directly the multimode fiber and generate the photons with a spontaneous four-wave mixing process inside the optical fiber instead of generating them in a bulk crystal and then couple the complex high-dimensional structure of the photons into the fiber. Then we use a long section of the same fiber to map the spatial modes of the photons to temporal delays. In this example, in anomalous dispersion, the bluish photons comes before the red ones, and low-order modes comes before high-order modes. Therefore, we can use the timer of arrival of the photons to reveal their spatial distribution, and also to reveal their correlations. Let's focus on our source for high-dimensional entangled photon pairs. Our source is based on coupling TISAF mode-lock laser pulses into a few mode fiber, and by spontaneous forward mixing process, 2 photons from the pump are annihilated to generate entangled photon pairs inside the fiber in 2 spectral channels, where each spectral channel is composed of different special eigenmodes of the fiber, as we can see here. To quantify the efficiency of the process, we measure the coincidence rate versus the pump average power. The coincidence exhibit quadratic scaling with the pump average power as expected from spontaneous forward mixing process. To quantify the coincidence to accidental ratio, we measure the coincidence histogram in different delays. And the coincidence to accidental ratio is defined by the peak versus the background, and we find coincidence to accidental ratio of more than 800. Next, we use a 1 kilometer long section of the same optical fiber, which serves as a mode sorter in the fiber-guided mode basis. Due to model group delay dispersion, the arrival time of the photons to the end of the optical fiber depends on their spatial distribution and their spectral channel. The photons are generated mostly in the few tens of centimeters of the fiber, after which the pump pulse is too weak for spontaneous forward mixing due to its temporal spreading. To investigate the model distribution of the 2 photon state, we use the mode-to-time mapping. Therefore, we plot the 2-dimensional histogram of the arrival times of both photons, the signal and the idler. 2 correlation peaks are observed corresponding to the 2 allowed spontaneous forward mixing processes. Clearly, this 2-photon probability distribution is not separable, indicating that the photons are correlated. Cross-section of the 2-dimensional histogram marked here emphasize the model correlation. For example, post-selecting events where the idler time of arrival is 0.4 nanosecond shows here localization of the signal arrival time around 3.5 nanosecond delay. Post-selecting of idler arrival time of 1.1 nanosecond show localization of the signal arrival time around 2.5 nanosecond delay. And the same is also true for post-selecting signal arrival time. In both cases, we can see that the localization of the idler photon arrival time. Next, we measure the delay between the 2 possible arrival time of the signal and the idler, and we calculate them numerically to show the validation of our model to time mapping. And I will show this in the next slide. In order to show that the measured delay match the expected delay caused by the model group delay dispersion of the fiber, we numerically calculate the model group delays after 1 kilometer section of the optical fiber. Therefore, we solve the scalar wave equation of our fiber, and we present the relevant fiber modes called LP11 and LP02 delays relative to the fundamental mode of the fiber. The fundamental mode of the fiber was chosen as a reference in order to cancel the chromatic dispersion. Now, if we look on the signal wavelength, we will find that the delay between LP02 and LP11 is 1 nanosecond, and in the idler wavelength, the delay between the LP11 and the LP01 is 0.5 nanosecond. These delays are in agreement with the measure delayed and the allowed spontaneous forward mixing processes inside the fiber. In conclusion, we demonstrated the generation and sorting of correlated photon pairs occupying high modes of multimode fiber. Our scheme opened the door for implementing high-dimensional quantum protocols over multimode fiber, since we solve the challenges of coupling single photons to high-order modes of the fiber. And also, our scheme is potentially solve the problem of the scaling of the number of the required detectors with the number of the fiber modes. Basically, because now we just need one single photon detector to measure the all possible coming eigenmodes of the optical fiber. For real-life application, boosting the performance is possible by using low-jitter superconducting nanowire single photon detector. The temporal resolution of the system is limited by the jitter of our single photon detector, which is about 400 picosecond. Now, the model group delay dispersion of the fiber is in the order of 1 nanosecond per kilometer. And therefore, 1 kilometer was sufficient for us to separate the eigenmodes of the fiber. But using low jitter superconducting nanowire single photon detector will allow sorting more transverse mode and using shorter fibers, and therefore also to decrease the background noise caused by the fluorescence. Finally, this is how our experimental setup looks in the lab. Thank you all for listening, and I will be very happy to receive questions or comments. Thank you.